Okay, picking up where we left off, we finished talking about the parting plane between the two die halves in an injection molding machine and how important it is to have draft angles. Now we're going to talk a little bit about the mold cavities. Okay, let me go back to this right here. So here we have our mold cavities, and in fact we have kind of four. Remember we talked about we have four different areas here, corresponding to 16 different shapes. I don't know exactly what's being made, but it looks like we have 16 different shapes here. The mold cavities are where we have to consider the geometry of not only the part, but how the gates and runners are going to be arranged. Now, one of the interesting things to note here, one of the difficulties, I should say, is the fact that you need to make sure your gates and runners are all of equal length from the point of injection to the actual part, right? So if you look at these, right? So letter A here, this radial star runner system, which it says is a poor design. I'm just using it for illustration purposes. This is the point of injection right in the center. So as we inject the plastic, it's going to go out through each one of these runners simultaneously, and we have to make sure that each runner has an equal length. If we have one runner with more or less than the others, then they're going to fill at different speeds, and it could cause problems with cooling. All right. So this is just an example of different types of runner systems. We have the star runner, which is going to have a better design than actually I have these are the same name, but this one is a better design. And that's because the plastic is going to split into two at this later point. Okay. So it's going to be better for that reason. Here we have, kind of an H branching system. All right. Here is another, this one is unbalanced, right? And unbalanced means that we have a much longer. So notice the length that the plastic has to travel to get to these outer parts is going to be this length plus that length, where for the inner parts, it's going to be the shorter length plus that length. Okay, so these are unbalanced, and that's not good. E is also an unbalanced runner system. And so that all goes into consideration on mold design. So there's definitely an engineering, a science involved with the mold design. And a lot of time and energy and money is spent on designing these very well. So looking more closely in at the runner design, we have different shapes for how the ejector pins are going to push the part out, different angles that we have to consider for the part, different geometry for the gates and runners, whether the runner or gate, I should say, is below or split 50-50, what the shape of the gate is, right? Whether it's going to be semicircular or modified trapezoidal, half round, rectangular. All that has an effect on the plastic part, on the creation of the plastic part. All right. Now, I don't want to scare you. We're not getting into too much detail here. In fact, I'm just going through this so that you can feel like we went into a sufficient depth. Your book doesn't really cover it to this degree, so this is kind of above and beyond. And this class is not about mold design or gates and runners, but just so that you have a more thorough understanding of injection molding. So some special features with mold design. We can have sliding molds. I don't think this is animated. Yeah, it is. Okay, so here, a sliding mold is what we use to get a feature on the side of the part. Now, if we were in class, I have a physical model of this, which would be kind of neat. But here, I'll try to explain it So the yellow is the part that we're creating. So we come down, we inject the material, and then we push it off. The ejection is going to happen on the top, which they're not showing that, but the ejection comes down here. But we want to create these holes on the side. And in order to do something on the side like that, we have this part right here. This is a slide. And notice that this pin is going to, by the angle of the pin, is going to push the slide in to create this side hole. So this is a really advanced and complex kind of thing here for multiple moving parts. Obviously, this mold is going to be super detailed, very expensive, but you know, the form freedom again is going to be phenomenal with this kind of design. Still looking at some special features. We have mold venting where we need to allow the release of air. Okay, so this is, if we look at this design right here, I think it's a little bit easier to see. So the gate, remember the gate is where the plastic comes in. So whenever you fill something, think of this as an area that you're going to fill with the plastic. This is where the part is. Right now, it's already filled. And it's filled with what? It's filled with air. So if we just squirt this plastic in here and the mold halves are tight together, we're going to be pushing against this air volume that we're not going to be able to push against, right? So the air is going to keep out the plastic. So one thing that we can create with our molds is we can create this venting system. And you see these different spokes around here. And these are basically for air venting. So they're small enough. Notice this, if we go over to the right, notice that they're small enough here. They're created so that they're too small for the plastic to get out of. They're basically too small for the plastic, but the air can escape out of this easily. All right, so this is mold venting. Now let's go back to this design and see if we can see any mold venting. I think you can see some right around here, right? That right there. So we can kind of see some mold venting here. This area right here is going to be mold venting. Okay, so we can kind of see it if you look closely. Here's another different way to do that, where you have perimeter venting. This is where we have the air venting, but we create a perimeter channel, right? So a lot of complexity in this. And like I said, I don't want you to worry that we're going to have, you know, your test is going to have a lot of questions on mold design. It's not. This is kind of just a cherry on top of on the sundae. All right, mold cooling is very important, right? So if we can speed up cycle times by cooling the mold, right? A chilled mold is going to allow for the plastic to cool faster, so decreasing cycle time. So what we do with the molds is we run water through it, right? So all this tubing right here is basically to run water through it, right? And you can see the channels in this semi-transparent. You know, we're going to run water through it, and so the mold is going to be chilled to some extent, and it's going to help with removing heat from the part so that we can create it that much faster, so we can reduce cycling time. What's really neat is their technology now to do what's called conformal cooling. Conformal cooling is basically taking these straight channels where the water is going to run and making them conform to the shape of the mold, okay, or the shape of the part. So this is more of a traditional mold where we have to create straight lines. Why do we have to create straight lines for the piping? Well, because we can only drill straight lines, right? These holes are drilled, right? Drill bits can only go in a straight line. So consequently, the mold, you can see in this area right here, in this area right here, the cooling is not going to be so great. Yeah, over here, where the cooling lines run close to the mold cavity, over here, again, where it runs close to the mold cavity, yeah, that cooling is going to be good, but not in the corners right here. And that creates kind of a problem. So now we can actually 3D print metal molds, right? So we can 3D print metal, and we can 3D print these complex shapes. Now, think about it. You can never drill this kind of a shape, right? This can only be formed with 3D printing. But now, because the channels conform to the geometry of the object that we're trying to create, the part, we can have much more efficient cooling for our molds. All right, so now let's look at some different types of injection molding. The first type we're going to look at is called insert or outsert molding. This is basically kind of like a double shot of injection molding. Maybe you can see it here on the right-hand side better. So we have this part this looks like aluminum, cast aluminum, and we want to cover it with a plastic, right? So we put that into the die, and then when we inject over it, it's going to create this blue shape. But then we want to have another plastic over that. And so this would be done with two different operations. Okay. There is a video that I've given you on Canvas which goes through all this, which shows. I think there's a couple that shows the insert and outsert molding very nicely. So. Please look at that if you're confused by this explanation or by these images. It's a very neat thing. Injection molding using gas injection. So what in this case, what we do is we have the molds that we inject the plastic into, but then we add a gas element to inflate and puff up the plastic so that it rests in the die and we get a hollow channel. Again, it's tough for me to explain this without a video, so please go to Canvas and look at the videos that I've included in there. This is kind of an animation that you'll see here. So we have the part is injected, the plastic is injected, and then we're going to inject a gas afterwards that's going to push the plastic out to the edges so that we create a hollow shape. Okay, let's look at that one more time. So the molds close, the plastic is injected, and then we inject a gas after that to fill the mold and to push the plastic to the outside, to the perimeters. Okay, 2K injection molding. The 2K is German. It doesn't stand for 2000. It just stands for 2K. K is component, which is, it just basically means that it's a two-shot injection molding process. We see it a lot, right? If you look around, you're going to see plastic parts with kind of a grippy plastic over a hard plastic. Okay, like in these cabling here and this handle. So this is invented by a German designer. That's why it gets the name 2K, but it's very common now. You can get different properties, different materials, and you can actually have up to 7K, 7 components, so 7-shot injection molding. I don't know, that seems kind of ridiculous, but you can have that much. All right. So again, more form freedom. Think about the applications where we have a grippy outer plastic with a hard inner plastic. A lot of I'm thinking of gardening equipment has that. All right. The last thing we're going to look at here is rotational molding. Right. So rotational molding is a type of molding that is used to create these kind of hollow shapes, right? These are reservoirs for different liquids, maybe gasoline, maybe something else, maybe water, right? But they are hollow in the middle, right? So we have this hard plastic outside and then a hollow in the middle. So how do we create that hollow shape? If you look over with this kayak, we also have a hollow shape. So if we disregard the opening here, we have a hollow shape on the kayak. Same for these chairs, right? These chairs are not solid. If you've ever used these, you know that if you cut them open, they're going to be hollow on the inside. So these are created with a process called rotational molding. And with rotational molding, basically what we're doing is we have our mold halves, right? This is one half of the mold, and then we cover it with the other part. We're going to put our powdered metal in here. So our, not metal, our powder plastic, right? So our plastic pellets are going to be placed in here. We're going to cover this up. And then this whole mold is going to be heated, right? And as it's heated, these pellets are going to start to melt. And as the pellets start to melt, what we're going to do with this mold is, yeah, you guessed it, we're going to rotate it, right? So we have to rotate it on a number of different axes. So basically, we're spinning it in all different directions, not necessarily fast. This isn't a fast spin. This is a nice controlled slow spin. And as it's spinning and the plastic is melting, the plastic is going to go to the outsides, and it's going to create this hollow shape. Right? And then we let it cool. And then we open it up and we have this hollow shaped plastic part. All right. So that's rotational molding. I have some videos in the Canvas site for rotational molding as well. It's really neat. And I think I have a video with them making a kayak. I thought that was kind of interesting because, you never think about how some of these parts are being made. Some of these structures are being made. A kayak itself has a lot of different plastic components in it. So you got a rotational mold for the outer, the body, for the, maybe even for the seat, right? Or it could be a hard plastic seat, which would be injection molding. Then you have this is probably created this plastic, like a neoprene rubber, cover right here is probably done with thermoforming. Okay. So a lot of different operations going on in here. All right, so that finishes up our discussion of Chapter 7, and it finishes up Section 2. Please, please, please look at the videos in Canvas. They'll really drive home a lot of these technologies and techniques so that you can better understand them. Don't be afraid to watch the videos and then go back to the PowerPoints. And in fact, if I was to suggest what you're going to be doing, I would suggest that you watch the PowerPoints and the videos simultaneously. So as you go through the different PowerPoints, maybe you're listening to me on this lecture, you can pause it and then go look at the video so that you see what the heck I'm talking about. All right, so that's it for Section 2. I will see you when we start Section 3, which is going to start our look at the forming or forging process. So a lot of excitement there. All right, I'll see you later.